Hi guys, this is 3.1. This is the intro to exponential growth and decay, meaning it's just an exponential function. So it's basic of the exponential function today. The learning goal is to know the characteristics of the exponential growth or decay. They're basically the same, but one works in the opposite way. So if you take a look at the first investigation, let's assume that your money grows double every day, and then your initial investment is $3. So I already filled the table for you. So starting from the 0, x is the number of days in this case, and the y is the amount of the money that you have. So starting from day 0, you have $3 to start with, and then day 1, it grows to $6 because it has to be doubled, and then becomes 12, 24, 48, 96 because it doubles again. Now, if you plot the points, now according to what I drew here, the grid wasn't really good enough to contain all these points, but if you actually draw a graph, what you can see is that as x goes this way, meaning x increases, your graph actually exponentially increases as well. It grows really, really quickly. And then as you can see it, as the x approaches to the negative infinity or goes to the left, the graph doesn't cross the x-axis. It just gets really, really close to the x-axis. So as the summing up, the graph grows exponentially as x increases, and then as x decreases, the graph approaches 0. In other words, it gets really, really close to 0 as x becomes very, very small number. But it will never become 0. It will always, always approach 0, but it will never become 0. Now, using the table of values above, find the first and the second differences to see whether it has the same pattern as our linear or quadratic functions. Okay, so let's find the first differences. I'll just put another column right beside the y, and then this is our first differences. So going this way, 3, 6, 12, 24, and then 48. And then since our first differences are not the same, so we have to go with the second differences. Now this is our second differences, so going this way again, it will be 3, 6, 12, 24. Again, now the second differences are not the same, so the one thing that you have to now look for is the ratio of the second differences, meaning from, let's say, the first column to the second column to the third column, and on. What is the number that you have to multiply or divide? Okay, it's easier for you to actually just remember as a multiply to get to the next column. So I will put another ratio right there, and then that will be my ratio. Okay, so the easiest possible way to find it is, remember the difference was 6 minus 3, right? We were going from the second column to the first column to find what the first and the second differences are. So all we have to do here is the same, but instead of differences, we have to divide. So 6 divided by 3, that means it's 2. 12 divided by 6, it is 2. 24 divided by 12, it is also 2. So this means that your ratio is times by 2. Okay, it's a multiplication of 2. So what we notice is that the first differences and second differences are not constant, right? They're not the same. But we have the ratio, right? But we have the ratio. So it says find the ratio of the second differences, and what we notice is the ratios are the same, right? So in this case, the equation of the table values is this. Okay, I set it up beforehand. Now our job is to find the similarity here, or the common, or what you can find actually from the relationship of the equation and the table of values here. So I have 3, and hopefully you notice that the 3 is our initial value, right? So whatever that's multiplied in the front of the exponential function is your initial value. So the 3 is initial value. Now, then what about the 2? Where do you see 2? I don't see 2 in the y's or FD or SD, but I see the 2 in the ratios. So this 2, we call it base of the exponential function, is the ratio. Okay, so this is an important part. So in a general form, if you have a times b to the power of x, this is the exponential function form. Your a is always the initial value. Okay, and then your b is always the ratio, that your exponential function follows. So remember that one, okay? Now then let's get to the next slide. It's about the same, but it's now slightly different. Now in this case, our there's an element, and its weight decreases by half every single day. So again, x represents half, or x represents the number of days, and then the y represents the amount of the element. So starting from 10, right? Starting from 10, because we start from day 0, and then it becomes half of it, becomes half of it, becomes half of it, and then on and on and on. Now 1.25 divided by 2 is, I believe, 0.625, and then this one divided by 2 is then 0.3125. Okay, so if I graph this, when it was at 0, it was at 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It was here, and then it becomes 5. Then it becomes at 2.5, and then it becomes at 1.25. So it's like somewhere here, and then at 4, it's somewhere around there. And I really can't point when the y equals 0.3125, so I will just put it that way. And then if you can see it, the graph actually goes this way, right? And then as the x goes to the right, meaning increases, my graph gets very closer and closer to the x-axis. And then as my graph goes to the left, it actually increases exponentially. So in this case, if you can notice it, the graph actually is the flipped, in terms of the horizontal way, version of the previous one. So that's a key important part. We'll visit that one a bit later. So the graph decreases, or decays, we sometimes say, okay, decreases exponentially and approaches 0 as x increases. And then as x decreases, the graph grows or increases exponentially. In other words, it gets very close to 0 as x becomes extremely large, but never becomes 0. So it's the opposite of the previous one, right? So same drill as before. Let's find the first and the second differences, and then try to find the ratio if they are not constant. Okay, so I'm just going to draw the 3 columns and then see whether we can do. Okay, so then we have the first differences, second differences, and then the ratio. We're not sure whether there's going to be a ratio to it, so let's do the calculation really briefly. So we have 5, we have 2.5, we have 1.25, we have 0.625, and then if you keep going, we have 0.3125 as the first differences. Now they are not constant, so we have to go for second differences. So then it is 2.5, oh sorry, negative 2.5. These are all negatives, right? All negatives, don't forget. And then this then becomes second differences of 2.5, 1.25, and then 0.625, 0.3125. Are we okay? Now, then, since the first differences and the second differences are not constant, then we move on to the ratio part. So the same thing. So then 1.25 divided by 2.5 is actually 1/2, or we can call it 0.5, but I prefer the fractions, but it's up to you, so we can call this a 0.5. Now, then if we do the same way and going this way, then it is again 0.5 or 1/2, and then it will be also 0.5 or 1/2. So what we saw from the first and the second differences is that, again, the first difference and the second differences are not constant, right? They change. And then if you find the ratio, they are the same, right? The ratio of the second differences ratio is the same in this case. So then let's try to match to find the characteristics of our function here. So we have y equals 10 times 1/2 to the power of x. Now, since the x is in the exponent part, this is the exponential function, okay? Now, the 10 in the front that is multiplied to the function, if you try to find it, this is your, hopefully you actually see it, your initial value, right? So this is, again, initial value. And then if you try to find the 1/2 or the 0.5, again, as the same as before, it is the ratio. Okay, so it is the ratio. So Again, always remember whatever the base with the exponent of the x, that's the ratio, and then whatever that's multiplied in the front to the exponential function is your initial value. Okay, so that was quite simple enough. Now, one thing that you have to remember of is the graph, and we'll visit that later. Okay, now then the next one. So the summary is this. Hopefully you remember this. A is the initial value, and B tells you whether it's increasing or decreasing. Now, when B is greater than 1, for example, when it was doubling, right? When it was doubling, the graph was growing this way. Do you agree? It was growing as x becomes large and large. But for the B becoming between 0 and 1, like A 0.5 that we did, was the half, right? I cannot say halfling. It will actually look, the graph looks like this. So it was actually decreasing as the x becomes larger and larger. So be really careful with this. Okay, don't get confused with the b part. Now, how to come up with an exponential function from a table of values. So as we did before, check whether the first differences and the second differences are not constant. Okay, if they're not constant, then take a look at the ratio of the second differences by dividing the first column by second column. So by doing so, you will be able to find the ratio, okay, if they're the same. Once you do that, then we have to use either the b or the x equals 0 in the table of values, and that becomes your a value. So whatever the y value when x equals 0, that is your a value in your basic exponential function. Now, the characteristics that we have to be careful of, again, is this. Since the graph is going either this way or going this way, we know that the domain is literally everything, all the real numbers, because it just keeps going. However, the range is slightly different because I forgot to put it here. But the range has to be y such that y is an element of real number, but y has to be greater than 0. Remember the graphs before? I told you that it gets closer to 0, but it never touches the 0, right? Or it never crosses the 0. So y has to be everything but greater than 0. Okay, so that is my range for the exponential function. And then two things that you have to remember of is listed in the 2 and 3, so make sure you remember those. Number 4, it is a curve either only going up or down. Okay, it's not that you're going in a weird way like a roller coaster, so it doesn't work that way. And then y-intercept is always at 0 comma 1 without any transformations, meaning when a equals 1, okay, and then there is no transformation in terms of the h or k, okay, none of these. Now, then your work is from page 156, 7 to 12. Now, before we move on to that, then you're going to say, you only talked about when b is from 0 to 1 or b is greater than 1. Then what's happening with when b is a negative number? You never talked about it. So let's do a couple of things. So let's say the b is negative 2. Okay, so b is negative 2 and then a is 1. So our function looks like y equals negative 2 to the power of x like this. Well, obviously there is 1 times, but we don't really have to worry about that 1 times, right? Timesing 1 is basically the same as not timesing anything. So this then becomes 1 using the calculator. This becomes negative 2, this becomes 4, this becomes negative 8, this becomes positive 16. So if you plot this out, when x equals 0, you have at 1. When x equals 1, you have at negative 2. When x equals at 2, you have at 4. And 3 at negative 8. So this is 2, 3, 4, 5, 6, 7, and 8. And then the 16, I can really draw 16. But what's happening here is that it goes up, down and up and on and on and on, right? So in terms of how it looks like is that it actually goes like that. And then in terms of this way, it goes like that. So this is called a harmonic function. Okay, this is not an exponential function. So exponential function's base cannot be negative because it doesn't have the properties of the exponential functions. Are we okay? Now, some of you may ask me then what's happening with when b equals 1? Well, it is basically y equals then 1 to the power of x. Well, 1 to the power of anything, let's say 1 squared, 1 to the power of 4, 1 to the power of 10, 1 to the power of 100, those are all 1, right? It doesn't change. So it basically is a straight line at y equals 1. So this, again, is not exponential function either, okay? So that's why in these two, I said b cannot be equal to 0, right? 0 to the power of anything but 0 is not is just either it doesn't exist. If the b is greater than 1, then it's increasing, and if b is in between 0 and 1, it's decreasing. So as long as you remember these, you should be okay for this section. Okay, so I'll see you guys in class. Bye.